Welcome back, everyone. We're going to continue on now with 5.5 again, but this time we're going to be graphing cosecant and secant. So the essential question today is, how do I graph cosecant and secant functions? As before, we're going to go ahead and copy down the library of parent functions, and we're going to write down exactly what they have in here, so go ahead and take a moment to do so. Now, the nice thing about cosecant and secant functions is that even though they look pretty unique with all these black curves going up and down, tons of vertical asymptotes everywhere, they're actually just based off of cosine and sine graphs. So we know by now that the graph of cosine as well as the graph of sine. We also know that cosecant is just the reciprocal of sine, and secant is just the reciprocal of cosine. Now, the whole point of having this reciprocal function actually helps us out a lot, because when it comes to graphing, once you know the graph of sine and cosine, you already know the graph of cosecant and secant, because they are just the reciprocal of that number. Okay? So we're going to go ahead and take a look at how all of this comes to play. Alright, so first thing I want to kind of show, it didn't really show that well in the book, but I'm going to be using purple and green, and the way that I'm going to be graphing is that I'm going to include the graph of sine and cosine. Eventually you will be able to just memorize how to hand draw cosecant and secant without referencing sine and cosine. But we're going to go ahead and use them today to help us really visualize it, just because we're familiar with sine and cosine at this point. So looking here, you notice that these points are really different from each other. And if I were to say that, this might be 0.5, well, the reciprocal of 0.5 would be 1 over 0.5, and that's going to be 2. So if I'm comparing this point all the way up here with this point, that's definitely the reciprocal of the other. So this whole reciprocal identity basically allows me to plot my points using this original function over here. If that doesn't help, then just go ahead and use the visuals to really guide us here. Okay, so let's go ahead and jump actually right into the examples. So example 1. I'm going to graph y equals 3 cosecant of x minus pi over 4. So basically, cosecant is the reciprocal of the sine function. So cosecant x is equal to 1 over sine x. So if I were to base my graph off of something I already know, I'm going to base it off of the sine function. So let's go ahead and do that actually. So I'm going to go ahead and sketch my graph in. Now, one thing you should notice is that cosecant, secant, cosine, and sine all have a period of 2 pi. For cosecant and secant, it doesn't really matter where you start, because, with any trig function, it doesn't really matter where you start. But for our sake, we will work from 0 to 2 pi, just to make it a little simpler. Okay? So first off, I notice here that I'm going to be amplifying by 3. So a is going to be equal to 3. And I'm going to have a shift right. So I'm going to be moving to the right by pi over 4. Okay? So I'm going to start off with a sine function that's amplified by 3. So let's go ahead and use that right now. 1, 2, 3. 1, 2, 3. And I know that sine at 0 is 0. But I'm going to go ahead and also shift it to the right. So technically, my starting point is at pi over 4. Okay? So from there, I'm going to go ahead and start plotting my next points. At pi over 2, and let's go ahead and label actually to make this a little easier. Pi over 2. pi, 3 pi over 2, 2 pi, and then basically anything in between will be some form of pi over 4. So shifting over to the right, normally at pi over 2, sine of pi over 2 would be 1, but being amplified to 3, it's going to be 3. But then I have my shift to the right, so I'm actually going to move to the right by 1. And then I have pi. Normally sine of pi is 0, so it's still going to be at 0, but I'm shifting to the right, pi over 4. Okay. Then, just continuing on, normally at 3 pi over 2, but then I'm going to go ahead, jump over 1, and go all the way down to -3. And then finally, I finished just past 2 pi. Sorry, please excuse the noise. We're going to go ahead and sketch that curve in now for the sine function. Okay, so if I were graphing my transformed sine function, that's actually where it is. However, as we noticed, we're actually graphing cosecant. Now, for cosecant, here's how I'm going to go ahead and graph it off of the sine function. Cosecant and secant have vertical asymptotes wherever sine and cosine are equal to 0. And that makes sense because if sine of x is equal to 0, and then we have cosecant of x being 1 over 0, that's going to be undefined. So basically, anywhere where sine or cosine have an x-intercept, that's where we're going to be undefined. So in this case, I'm going to be undefined here, here, and right here. So 3 vertical asymptotes, kind of restricting where our cosecant function will be. From there, cosecant is just a reciprocal function of sine, so I'm going to be in between here. It's going to be touching right at this point as well. And then from there, it's just going to curve upward. So if we were to say the opposite, that's not necessarily true because opposite refers to the signs, but this is the reciprocal of this guy. Over here, same thing. We have our point right there, and then reciprocal this way. Okay, and that's actually it. So the green portion is the graph of 3 cosecant x minus pi over 4. So we amplified by 3, shifted over to the right by pi over 4, and there's our graph. Now, you are allowed to go ahead and just memorize the cosecant function exactly as you see it. So a parabola-looking thing going upwards, a parabola going downwards, and you can transform it that way. But for me, because we've already introduced sine and cosine, I wanted to go ahead and use that just to show you guys exactly how they're connected. We're also going to go ahead and do that same thing for example 2, where we graph the secant function. So this time we're going to have y equals -4 plus secant of 2x. So with this one, we do have a vertical shift. Let's go ahead and note that. Vertical shift, as well as a period change. Okay, so those are the two that we're going to deal with in this problem. And in this case, it might be a little easier to draw out the parent function to begin with to kind of see what's happening. So again, I'll go ahead and show mine for reference. So this is the parent function, secant of x, the green portion. The purple is cosine, the original that we've worked with before, secant being the reciprocal function. Okay. So with example 2, what we're going to see is that we're actually going to, let me put this back up, we're going to move all of these points down by 4. We're also going to restrict our domain, our period actually, into a smaller region. So instead of being all the way going from 0 to 2 pi, we're only going to go from 0 to pi. So all of this is going to be compressed into a much smaller little region, so from there to there. Okay, so with that mental image, let's go ahead and try to graph this without having the parent function right there. So I'm going to make it a pretty big graph because I know we're going to go down quite a bit. Going to be mostly in the negative region. And now I'm going to go ahead and try to make it consistent with the scaling that I have up here. So if this is pi over 2, this will be pi, 3 pi over 2, and 2 pi. Just to have that visual imagery, okay? For our period, just to show a little bit of work, we started off with a period of 2 pi, but we're going to be dividing by b, which is going to be right there. So 2 pi over 2 will be pi. We're going to divide pi into 4 equal parts. So we're working within pi, and I need to make 4 equal parts. So now I'm going to have pi over 4 and 3 pi over 4, squeezing that in right there. So my entire function will fit only within that small little region. Okay? Now, let's go ahead and start graphing. So the first one I'm actually going to graph is my cosine function, just because I'm familiar with that. I know that at 0, cosine starts off at 1, but because I'm taking a vertical shift of 4, I have to move it down. So 1, 2, 3, 4. So all the way down to negative 3. And then starting at pi over 4, we're now going to be back at 0. So I'm going to go down 1, 2, 3, 4. At pi over 2, we're going to go down all the way to negative 1, and then a vertical shift of negative 4. So 1, 2, 3, 4. 3 pi over 4, back at 0, so right there. And pi, we're going to go back straight up to 1, so at that point right there. So if I were to sketch in my cosine function, this is what it will look like. And now I need to keep in mind where my original x-intercepts were. They were right here and right here at 3 pi over 4. Okay, so that's my cosine function, but what I really want is my sine function, my secant function. So let's go ahead and start here at this point, and this point. Because these are vertical asymptotes, my secant function will go ahead and ride along there. So this is kind of like the vertex of it, and then we're just going to go up right along the vertical asymptote over here. And go ahead and have our parabola going downwards here, all the way down, right along the vertical. And then finally, the last portion will be right there. And just like that, you have drawn one full period of a secant function that's been transformed with a vertical shift of negative 4 and a compression with that frequency change of 2. So we compressed it into this tiny little space. And let's go ahead and compare it how it looks to the original parent function. So up here, this is about where we're starting. So we moved it down and we compressed it. So that's really all there is to it. Hopefully this video made more sense than the previous videos, and because we're getting more and more used to it, it just all kind of connects a lot more now. All right? So rewind, replay as you need to. Otherwise, go ahead and move on to the Google Forms once they are posted, and have a wonderful weekend, you guys.